Rotations, dilations, and symmetry. When we rotate about a point. In the coordinate plane, typically we rotate about the origin. Rotating any angle at all is fairly difficult. You have to imagine this being a radius of a circle and moving around that circle. And if I give you some weird angle like 35 degrees, it's a little tricky to do that. But there are some rotations that are fairly easy to do, specifically 90, 180, and 270 degrees. Let's figure out how to rotate this point, the point 4,2, about the origin. And before we do that, let's point out that counterclockwise is positive. That's a positive degree angle, like the arrow shows. And we're going to rotate this 90 degrees. To do that, we can use the slope. We see that if we start at the origin, that we go up 2 and over 4, rise over run is 2 over 4, which is 1/2. Now I'm going to stick with 2 over 4 because when I rotate, the distance, that r here, isn't going to change. I'm going to use the slope -4 over 2. So from the origin, I'm going to go down 4 and over 2. Now what you have to understand is I just made a perpendicular. A rotation of 90 degrees, right there, is on that line I just drew. But we have to preserve this length. The length isn't going to change. That r, that's the radius of a circle, is not going to change when I rotate about a point. To figure out where it is on this line I drew, what I can do is take this slope right here and move the negative to the bottom. Understand that -4 over 2 is the same thing as +4 over -2. They're both -2. And if I start at the origin and I rise +4 and run -2, I get right here. And notice that if you look at the triangle that's right here, it's exactly the same triangle. It's a right triangle with a leg of 2 and a leg of 4. And the hypotenuse then would be exactly the same. This r is the same. This is a rotation of 90 degrees. Now take a look at the ordered pairs on that point. The ordered pairs are -2 and +4. Look at these points. Notice what happens. When I rotate 90 degrees positive about the origin, a point xy becomes, do you see how 4 became -2? So the x became the y, but not only that, it became the opposite of the y. And the y value, 4, is sitting right there in my original point, but it's the x. A rotation of 90 degrees takes a point xy, and it becomes -y, x. What about a rotation of 180 degrees? I can use those same lengths, that's the 2 and the 4, to figure out where I'm going to be on the other side. It's going to be along that line, 180 degrees. If I go down 2 and left 4, let's draw this in. You see how the legs of that triangle are still both 2 and 4? And notice again, I went 180 degrees. And these two lengths from here to here and from here to here are exactly the same. This is a rotation of 180 degrees. It's always along a straight line through the point of rotation and the same distance on the other side, because this is a radius of a circle. I have an r here and an r here. And a point, 4, 2, it becomes the point -4, negative 2. So rotating 180 takes a point xy and makes it negative x, negative y. When I rotate 270 degrees, that would look like that right there, and back on that black line that I drew. Again, I'm going to use the lengths 4 and 2 to make sure I get that same R. I'm going to go down 4 and over 2, and I'm right there. And take a look at that triangle. Notice it's the same triangle. There's the 2, and there's the 4, down 4, but it's still a length of 4 and a length of 2. And this R right here will be exactly the same. Let's look at that ordered pair. It is the ordered pair 2, negative 4. If we rotate 270 degrees, the point 4, 2 becomes 2, negative 4. That means that xy becomes the 2 from the A, point A, is now in the x spot. So the x becomes y, and the 4 in the original point becomes a negative 4 in the y spot. It becomes negative x. You will use these on questions in the homework. Each question, though, will provide these hints. A dilation is a transformation in which a figure is either made bigger or smaller. It's expanded or contracted. What that is determined by is called the scale factor or sometimes the magnitude. When we do a dilation in the coordinate plane, it turns out to be very simple. A dilation with, say, scale factor of 2, we can't go very big on this scale factor because we'll need a really big graph, but 2 is manageable. What happens is the point A, 3, 0, becomes the point A prime, the new location for A, and I just multiply both by 2. That's 6, 0. B, which is the point negative 1, 2, when you multiply by 2, becomes B prime, which is negative 2, 4. And C, the point negative 2, negative 2, when you multiply by 2, becomes C prime, negative 4, negative 4. Let's plot these points. 6, 0, negative 2, 4, and negative 4, negative 4, and draw the lines. Notice how the transformed figure that is dilated by 2 in red is similar, has exactly the same shape. And if you were to measure, you would discover that each side would be twice as long. The area, however, I will point out, because both the length and width are increased by 2, and area is length times width, the area of the figure in red is actually 4 times the area of the triangle that's in black. Keep in mind, the scale factor could also be a fraction. It could be 1/2. In that case, you'd have a figure that each side was half as big, and the area would be 1/4, 1/2 times 1/2. We're going to look at two kinds of symmetry, line symmetry and rotational symmetry. Symmetry exists if basically there's a transformation that maps the figure to itself. For line symmetry, the thing we're looking for is, can I draw a line where the reflection on each side of the line would match each other? Could I fold the figure over the line and would it match up with itself? For an equilateral triangle, what you need is the midpoints of each side. Then, from each vertex, draw a line through the opposite midpoint. Notice that an equilateral triangle has 3 lines of symmetry. For a hexagon, there are 6 lines of symmetry. I can draw lines through each of the opposite midpoints, and that will give me 3 lines. Then I can draw lines through each of the opposite vertices. There are the 6 lines of symmetry for the hexagon. A pentagon has 5 lines of symmetry, from a vertex through the midpoint of the opposite side. There are the 5 lines of symmetry for a pentagon. A rectangle has 2. We need the midpoints of the opposite sides. Remember that with line symmetry, a reflection over the line you draw should map the figure to itself. Rotational symmetry means that there's a point I could rotate the figure about and match it up with itself. The order of the rotational symmetry refers to how many times I can rotate the figure to get it back to itself, to get a full 360 degrees. If you find the center of each regular figure and rotate about that point, it all comes down to these triangles. Notice that this one would be 1/3 of a circle, 120 degrees. This one here would be 360 divided by 6, which is 60 degrees. For the pentagon, this angle would be 360 divided by 5, which is 72 degrees. These are the angles of rotation: 120 for an equilateral, 60 for a hexagon, and 72 for a pentagon. The order then for the equilateral triangle would be 3 because I could rotate it 120 degrees. I could rotate it 240 degrees. That's another 120. And then another 120 would give me that 360 degrees. The order is 3. For the hexagon, I could rotate it 60. I could rotate it 120, 180, keep adding 60, 240, 300, and finally that 360 degrees. Notice that there are 1, 2, 3, 4, 5, 6 different angles of rotation. The order is 6. For the pentagon, I could rotate it 72 degrees, 144 degrees. Another 72 would be 216 degrees. Another 72 would be 288 degrees. And then 360 degrees. 1, 2, 3, 4, 5. The order is 5. For the rectangle, it has, around our center point there, 180 degrees rotational symmetry. If I rotate it 180, it matches up with itself. That means the order is 2 because I could rotate it 180 and I could rotate it another 180, which would make it 360 degrees. The angle of rotation then is 180. The last thing I need to point out about rotational symmetry is that every figure has 360-degree rotational symmetry, so it does not count. If that's all you have is 360 degrees, then you don't have any rotational symmetry. The rest of this video is questions from your assignment. Question 1. Is this a rotation or not? If you pick 2 corresponding points, and you look at the angle created with the origin, notice how this line, I go down 2 and left 1, so the slope of that line is -2 over -1, which is 2 over 1. And the slope of the other line, which actually looks to be 90 degrees, I'm thinking that's the perpendicular slope of this. The perpendicular slope, reminder, is the negative reciprocal. It would be -1/2. You could also put the negative below, 1 over -2. And notice that if I do this right here, I go up 1. Okay, here I'm at the origin. Let's change colors. I go up 1 and run -2, -2, or there I am. In other words, what I'm trying to tell you is that this and this are perpendicular. This is a 90-degree rotation. It is definitely a rotation. I mentioned that some rotations are easy to do. We just need to follow the correct formula. We're going to take xy and make it -yx. So the y, which is 0, becomes the opposite and goes in the x place, still 0. And the x, -2, goes in the y spot. 0, -2, take the y value, make it the opposite, put it in the x spot, that's 2, and the x goes in the y spot. -1, -4 becomes 4, -1, and -5, -4 becomes 4, -5. Let's plot those points. And there's our rotation of 90 degrees about the origin. Question 5, we're going to rotate this 180 degrees about the origin, which means we're following this formula right here. I've labeled our points and figured out all the coordinates. Now I'm going to apply this formula. Xy will become -x, -y. So take the opposite of x, that's 2, and the opposite of y, -4. And repeat that. This will become 1, -1. This one will become 2. The opposite of 0, still 0. This one will become 4, -3. Let's plot those points. And it looks like that. This is a rotation of 180 degrees in the positive direction about the origin. Question 7 is a rotation of 270 degrees about the origin. Counterclockwise, that's the positive direction. We're going to follow this formula. I've labeled our points to make it easier to understand. I came up with all the ordered pairs. Now I'm going to follow this. A will become A prime, and from this ordered pair, I'm going to put the y in the x spot, that's 0, and I'll put the x in the y spot, but make it the opposite, that's -3. B will become B prime. I'll take the y and put it in the x spot, and put the x in the y spot and make it the opposite. C will become C prime. 2, 5 will become 5, -2. D will become D prime, and 1, 2 will become 2, -1. Let's plot those. There is a rotation of 270 degrees about the origin. Question 16. Identify this transformation as reflection, translation, rotation, or dilation. Notice how each figure is similar to the other. It's just bigger or smaller. This is definitely a dilation. A dilation makes a similar figure. Its size determined by the scale factor. Question 17. Describe the dilation of the point to its image. 1224 is becoming 3/6. You're trying to figure out the scale factor. You're trying to figure out what you multiply 12 by to make it 3, what you multiply 24 by to make it 6. I'm calling that x. Notice that if you divide both sides by 12 and divide both sides by 24, you see that 3 over 12 and 6 over 24, that either way, x is 1/3. Our scale factor is 1/3. When the scale factor is less than 1, the figure will be smaller. This is a reduction. Question 18. What's the scale factor for this dilation? Notice how 4 becomes 12. I multiply 4 by something, call it x, to make it 12. And I take 3 and I multiply it by something to call it x to make it 9. Notice if you divide by 4 and you divide by 3, both of these produce the same thing, an x of 3. The scale factor is 3 to 1, or 3. This is an enlargement. Question 20 is a dilation, and we're going to do a scale factor of 3, which means every ordered pair will get multiplied by 3. A will become a new A, we'll call it A prime, and it'll be 9, 6. B, negative 1, 3, will become B prime, multiplied by 3, negative 3, 9. C will become C prime, and it is negative 6, negative 3. Plot those 3 points, and we have a dilation of scale factor 3. Each side would be 3 times as large, and because both the length and the width are 3 times bigger, the area would be length times width, 9 times bigger. Question 21 is a dilation with the scale factor of 1/2. A would become A prime, and we multiply 2 and 4 by half, which means we just divide it by 2. We get 1, 2. B would become B prime, multiplied by a half. That's divided by 2. We get negative 3, 3. And C would become C prime. If we multiply it by a half, we get 1, negative 2. Let's plot those 3 points. And we get a dilation of scale factor 1/2. Each side would be half of the original, and the area, since it's measured in squares, which have a length and a width, and each length and width is a half the size, the area would be 1/2 times 1/2, or 1/4 the size of the original figure. Question 31. How many lines of symmetry does this figure have? Well, there's no way to draw a line that I could fold the figure over. This one has 0 lines of symmetry. Question 32. This looks like a tear. Does it have any lines of symmetry? I see one line that I could reflect the figure over that line and match it up with itself. Question 33. We have a smiley face. Are there any lines of symmetry? Apparently, I could go right up between the eyes and that line there. If you fold it over that line, it would match up with itself. This one also has one line of symmetry. Question 35 is rotational symmetry. Rotational symmetry is when you rotate about a point, and this is a regular pentagon, it looks like, and the angle of rotational symmetry would be that angle right there. If I rotated that angle, the figure would match up with itself. That's 360 divided by 5, which is 72 degrees. Question 36. Does this figure have rotational symmetry? If it does, what is the order? If we go right to the center of our equilateral triangle and we draw in this angle right there. That is 1/3 of a circle. If I rotated this 360 divided by 3, or 120 degrees, it would match up with itself. And the order refers to how many times you can rotate it and get it back to 360. So I could rotate it 120, 240, and then finally 360. This one has order 3. 1, 2, 3. Question 37. Does this one have rotational symmetry? Well, I need to point out that everything has 360-degree rotational symmetry, and that does not count. So that's not rotational symmetry. This one actually does not have any rotational symmetry. It's DNE for both. It does not exist.